Setting up for the last contributor talk of this workshop. So the work comes from Peking University and it will be presented by Jiangyu Huang. The name of the talk is Effective Master-Slave Communication in a Multi-Agent Deep Reinforcement Learning System.
Good afternoon. I'm Xiangyu Kong from Peking University. Our work is about exploiting an effective master-slave architecture to solve multiple agent communication problem in deep reinforcement learning. Recently, deep reinforcement learning has become popular in many important AI scenarios. However, in most useful cases, we are often dealing with multiple agents. For example, in the scenario of autonomous driving, we will eventually be dealing with multiple auto cars instead of just one of them. For industrial robotics, multiple robots are working together at the same time to perform tasks. The same spirit applies to our video surveillance network and many other scenarios. When multiple players are playing together, we know they will communicate in order to collaboratively win the game. Therefore, one key question in a multi-agent IR system is how can we facilitate effective communications among agents. Moreover, such communications cannot be predefined due to the complexity of many real tasks. Due to these challenges, how to construct effective communication design is unsolved yet. Another important observation is that when multiple agents are performing a task at the same time, we often need a relatively global plan to achieve the best out of all. Therefore, how to plan in a global optimal manner in scenarios involving complex agent combinations is a very challenging open problem. Free work has been done in the regard. In previous work, the communication between two agents have been explored. One is Foster et al., another one is Gong et al. Both of them propose a communication channel between two deep queue networks. This channel facilitates the learning of cooperative policy of two agents to achieve a common goal. However, it would be computationally intractable if there are connections between every two agents. Just imagine how many channels this P2P-like architecture will need with the growth of agent number. There would be a communication explosion for a complex multi-agent system. Another branch of study relies on a common channel for multi-agent communication, such as BikeNet proposed a bidirectional RNN for the purpose, and ComNet uses the mean of each agent's message communication. An intuitive idea would be to move one more step to build a hierarchical structure where there is an independent agent, the master agent. This master agent will be in charge of multi-agent communication. It also works as a global planner to incorporate high-level thinking to low-level agents. This scheme is actually a master-slave architecture that has been utilized in several traditional problems, but very in deep reinforcement learning. Note that there will be no such a problem of communication explosion since there will only be linearly growing channels with more agents joined. Thus, we propose our master-slave architecture for multi-agent deep reinforcement learning, as shown in the right figure. However, there will be a problem if the master agent can only broadcast the same message to all agents, like ComNet. To resolve it, we propose a gated composition module showing the left figure to merge master action with slave actions. This will enable different messages for different agents with an input of each agent's own hidden state. To be specific, assume the master agent is implemented as LSTM cells. Its output C and H will be selected by the gating signal which comes from each slave agent to generate a particular action message from master to this agent. Then this agent's specific action for master will be element-wisely added with each slave's own action to produce the final action. Compared to the closely related ComNet model, our GSM model differs in these aspects. It uses an action merge module for communication. It also enables agent-specific message passing. And most important, we have a Scrum Master agent to generate high-level thoughts, while still allowing each agent's independent decision-making. Note that this master-slave architecture is also closely related to hierarchical reinforcement learning, in the sense that both has a meta-controller to generate high-level messages to low-level agents. However, in hierarchical reinforcement learning, the meta-controller can command one single agent work towards sub-goals sequentially and finally achieve the ultimate goal. While in the case of our proposal, the master agent controls multiple concurrent agents at the same time scale to work collaboratively towards the common goal. Reward is defined as the difference between the number of units and enemy units within a certain range of each unit, and there will be a terminal reward to mark the winning or failure of one-round combat. And the corresponding policy grading update is given as the below formula shows. To evaluate our proposal, we perform experiments on several representative multi-agent tasks, which include 2 discrete game, traffic junction, and the combat task defining a previous work, ComNet. We also select 3 challenging StarCraft micromanagement tasks, whose action spaces are continuous and are based on Torchcraft platform. For state representation, we utilize a grid like plan to encode the individual information of agents that falls in each cell within a predefined range. We utilize different implementation for discrete and continuous action spaces. Discrete actions are performed with a traditional policy gradient method. For continuous actions, we adopt a Gaussian policy formulated like this with a noise turbine. On these tasks, our method outperforms all the other baselines. Interestingly, the version with GCM only improved significantly on the task of 50 marine versus 60 marine. This is because only in this task, the dispersing movement of units is critical for defeating enemies, which is enabled by the proposed GCM module. As for the learning process, the proposed method also converges more quickly compared with the ComNet baseline on 3 tasks. An interesting observation is that while ComNet sometimes meets the targets, the master agent in our proposal does help by directing the slave agents to move towards the enemies and thus limit them. The slave agents will still have their own movement to make micro adjustment of their position. Here we show a successful policy learned by our model on the combat task. With the guidance of master agent, all the slaves gather together and focus their fire to defeat enemies finally. And this page shows how our board defeat the enemies in StarCraft micromanagement. The Marines learn a policy to spread very fast and kill frontier enemies and kill all others. Note that although we have less units than the enemies, our board can still defeat them. In conclusion, we propose a novel master-slave architecture for multi-agent deep reinforcement learning. Master agent will work as an effective communication channel for agents and give global planning instructions to low-level agents to help them achieve the common goal. This proposal tackles the problem of group-level collaboration in a new way and outperforms existing algorithms significantly. Thank you.